de katkı yapmak için ilgili noktalarda YouTube'dan izliyor olacağız. We will be maybe the listeners would like to know what we say. We are from the organizing committee, Dr. Erginer and also Dr. DANIŞMAN, but the chairman is Dr. DANIŞMAN. We will visit maybe other times. We will be watching their presentation in YouTube. Mr. Wei and Göksu and other coming have a good and nice presentation. Hope to see you, meet you again.
Yeah, definitely.
Hocam başarılar.
Teşekkür ederiz.
Teşekkür ederim hocam. Sağ olun. Mr. Wei, I guess, are you the presenter of the next paper?
Yes. Yeah.
Okay.
Okay, I'll share the screen now.
If you like to wait for a couple of minutes more, maybe up to 7 o'clock.
No problem. Yeah.
We have 6 minutes, so there might be some more attendees.
Yeah.
Okay, I'd like to say welcome again to everyone. This is the today's last session. So we'll start with Mr. Wei. He will present their study about the behavior of a crew transfer vessel in hot seas. and they apparently used OpenFOAM in this study. The co-author of this study is Mr. Tezdogan, Dr. Tezdogan, sorry. Would you like to introduce yourself with a couple of words, Mr. Wei, and you can start immediately.
Yeah, thank you. Good afternoon, guys. My name is Yujia Wei, and my supervisor is Dr. Tezdogan. I'm a second-year PhD of the Department of Anatomy in the University of Strathclyde, and we are more our research interest is about hydrodynamics and fluid structure interactions of container shapes or different shape holes. And in this study, I will present something about crew transfer vessel numerical modeling using OpenFOAM. Yeah, I think can start maybe.
Yes, please start. Thank you.
Thank you. So my research topic is use a CFD study on the behavior of a crew transfer vessel using OpenFOAM. Here is my presentation agenda. I will give introduction, then aims and objectives, and some numerical sightings, a verification and validation study, then result and conclusions. So as the fast growth of offshore wind industry, there will be more offshore wind farms demonstrated throughout the world. In order to reduce the overall cost about the wind farm, providing efficient maintenance is one of the key factors. So the crew transfer vessel was playing a role to transfer the technicians from onshore to offshore platforms. In Figure 2 is a crew transfer vessel at docking option layout. From the figure that the technicians were transferred from shipboard to platform ladders. So large motions, exponentially vertical accelerations of a ship, will cause serious accidents. In order to avoid that, some operation limits were cited by the classification societies. Three of them are listed. The first one is the vertical accelerations should be less than 0.15 gravity of accelerations. And also the second one is related to the wave conditions. The maximum significant wave should be less than 1.5 meters in practice. The third one, pitch motion and roll motion should be less than 4 degree and 6 degree respectively. Here present the aims and objectives of this study is to use a numerical model to investigate on the seakeeping characteristic about the crew transfer vessel at high seas. And afterwards, a verification and validation study will be presented to build the confidence of use of the numerical model. Then the critical working conditions will be studied. First, I will explain the shape. In this in this study, we use 18.5 double hull catamaran with low draft, and to reduce the resistance to support the fast transportation ability. But the fast speed and low direct angle will cause a sliming phenomenon and will further violate the ship motions. To achieve the geometrical similarities, we need to make sure all the length measurements for the model and the wave has the same skew ratio between a full skew and the model skew. The Reynolds number in this study is quite high, so turbulence model is implemented. The numerical method we use is basing on the finite volume discretization to solving incompressible Navier-Stokes equation as shown in equation 2. And we use volume of fluid technique to capture the air and water interface shown in equation 1. A symbol of alpha is, shows when it's equal to 1, it represents to water. When it's equal to 0, it presents to air. And in the between, an interface will exist. The equation 2 and equation 3 will be solved and to create a momentum pressure predictor by solving the matrix, use different numerical schemes. And those things can be resolved the flow field problems. The hydrodynamic forces can be calculated by integrating the flow force and the wave force onto the structure surface, and then by solving the ordinary differential equations shown in equation 4. So the fluid solver, we use its interform. Structure solver, we use a 6DUF rigid body solver, and for each time step, this loop will repeat again until the convergence achieved. So for the computational wave domain, it's very important to provide the boundary conditions to solving the differential equations. We summarize the boundary conditions we use and change the parameter, it according to the turbulence model. And the wave domain size was regulated by our fluid solver waves2form, which we use one wave length in the front of the ship bow and 1.5 length far away from the ship's stern. For the lateral boundary, we left at least one ship length away to avoid the wave reflections. The wave generation is quite important factor for wave structure interaction problems. In this study, we use Stokes-2 wave. It has an equation showing equation 5. We use this because of the accurate wave amplitude plus the consideration of nonlinearities. Match convergence test was presented here. We use 4 different match densities, and the results showing that for the medium match, which we divided wave height to 12 cells, have a good accurate result, and also balance the computational cost. So we use this match density throughout our case. The match we create by using the default OpenFOAM match generating tool, SnappyHex match. It's called SnappyHex match. It uniformly cut the background mesh and refine some important region, for example, free surface and the flow surrounding structure zone. Then those cells will be snapped onto these structures. Because in this case, we use turbulence mode of K omega st, so we have to pay attention to the Y plus value. We keep it into the log region, which is fluctuated at the value of 50. So every simulation was run on the Archie HPC with 40 cores. The constant time step we choose is 0.022 seconds. For each case, it needs 5 days to solve until to the 30 seconds to the stable result. Afterwards, we present GCI uncertainty test. The result from 3 different match densities and 3 different time steps were presented. It can the arrow calculation was shown in table 4. It shows a good convergence, but except the heave result in the time step, we believe that this divergence case is because the maximum time step we choose is too large. It cannot resolve the flow field properly. So the result was shown in the figure 9. In the first 2 are the fairly sensitive wave of heave and pitch motion, and afterwards is the force calculated, including wave force at horizontal and the vertical directions. Then the numerical result were compared with the experimental result, and the frequency analysis was showing the heave transfer function. The catamaran was high sensitive for the wave amplitude and wave frequency. The critical wave frequency is at 0.5 Hertz, according to the regulations as we discussed before. Here, the animations of the numerical model, and we can enrich many results. And the figure 12 showing the velocity plot. it can be found as an ignition point in front of the shipboard. And when the wave is approached, the velocity of wave between two dummy hull was slightly higher than the surrounding zone. It can be shown that this numeric model can plot high-resolution result. So here's the conclusion of this study. It's mainly on the CFD code is capable of predicting the shape motion with rigid body assumptions and the wave load at the specific wave frequency range. And we will extend this model for future studies, for example, irregular waves, parametric studies, sliming, hydroelastic studies. It depends on what we need. So here's everything we prepared for this study. If you've got any questions and comments, are welcome. Thank you.
Thank you very much, Mr. Wei. It was very nice presentation, and the results were charming as well. I believe they are very good agreement with the experimental studies. I know it's not easy to overcome this kind of problem in CFD, because you have to deal with all sorts of grid generation and convergence and other problems, and it will take quite a lot of time, even if you use much cores, such as 40 in your case. But I think it's a good job. Thank you very much with this nice presentation. And if there is any question from the audience, please don't hesitate and ask your questions. I think there is not any at this moment. Okay, thank you very much. We can proceed with the next presentation. Next presentation, I believe, will be presented by Mr. Ölmez.
Yes.
He's here.